Welcome back to the deep dive. Today, we're finally here. We conclude our multi-week exploration into the geometry of computation, charting those boundaries between what's easy and what seems, well, impossible.
We've set the stage. We've talked about P, that whole realm of problems with efficient, polynomial time solutions.
And NP, the much bigger, stranger space where you might not be able to find a solution easily, but if someone hands you one, you can check it in a flash.
Exactly. And today is the grand finale. This is where it all comes together. We're doing a deep dive into the concept that links all the hardest puzzles, NP completeness.
This is the concept that really clicks the entire landscape of complexity into focus, isn't it?
It really is. The NP-complete problems are demonstrably the hardest problems you can find within NP. And the promise here, the foundational idea, is just monumental.
The idea that if you, the listener, could find an efficient way to solve just one of them,
then that single method could be translated mechanically into an efficient solution for every other problem in NP. We're talking thousands and thousands of critical puzzles.
across every field imaginable: science, logistics, planning, everything.
Everything. Now, the source material for this final deep dive, I have to say, it's exceptionally dense.
We're moving past the simple definitions now. We're getting into the core theorems of complexity theory, the really technical proofs of what we call reduction.
Yeah, these are proofs that bridge completely different fields of math. They connect logic to graphs, graphs to arithmetic. It's like creating a mathematical Rosetta Stone between them.
So our mission today is to unpack these very formal, abstract constructions, to take these proofs that are based on Turing machine behavior and propositional logic and turn them into, I don't know, concrete, understandable aha moments.
We want you to see the gears turning, to see the actual mechanics behind how a computer scientist can prove that two problems that seem worlds apart, like, say, optimizing a delivery route and analyzing a protein folding, are, at their core, the same problem in terms of difficulty.
And this entire story, this whole universe of hardness, it all begins with one single discovery. We know NP problems have solutions you can check quickly. NP-complete problems are the master keys, or maybe the central bottleneck.
A bottleneck is a great way to put it. And we have to start with the original key, the first domino that set off this entire cascade, the satisfiability problem, or as it's known, SAT.
Okay, let's dive in. The Cook-Levin theorem. This is the origin story of hardness.
It absolutely is. Formally established back in the early 1970s, the Cook-Levin theorem is the cornerstone of NP completeness. It proves definitively that SAT is NP complete.
And what that means, just to be crystal clear, is that every single problem in NP,
Every single one. Any problem where you can quickly verify a proposed solution can be reduced to an instance of SAT, and that reduction can be done in polynomial time.
It's funny, the sources mention that when Stephen Cook first published this proof in 1971, it was kind of buried. It was in the proceedings of some obscure symposium.
That's right. The sheer magnitude of what he'd done, this idea of the equivalence of hardness, it wasn't immediately recognized. But once the field caught on, it was like discovering the theory of relativity for computation.
That's a great analogy. It provides the whole framework. So let's unpack the mechanism. How on earth do you turn an entire computational process, a Turing machine, running, stepping through time, reading, writing, changing state, into one single gigantic logical formula that's just true or false?
It feels impossible, right? Like trying to compress an entire movie into a single pixel.
Exactly, or a whole game of chess into one yes or no question.
The brilliance is to stop thinking about it as a process in time and start thinking about it geometrically. The proof looks at the entire computation as a massive table, a matrix. And the size of this matrix is bounded polynomially in the size of the input, let's call it law. So the dimensions are something like ppn by p(n). We're building a snapshot of time and space.
So each row is a moment in time.
Exactly. Each row represents the machine's entire configuration at a specific point in time. Row dollars is the state of affairs after I-1 steps.
And the columns.
The columns are space. Each cell in a row represents the content of the tape at a specific position, just stats. And the row itself has to encode everything. What's on the tape, where the head is, and what state the machine is in.
Okay, I'm with you.
Yeah.
But SAT is about logic. True, false. So we need Boolean variables to describe every possible state of every cell in this giant matrix.
That's the leap. If we can define those variables correctly, then finding a satisfying assignment, a way to set them all to true or false that makes the whole formula true, is the same as finding a valid, successful computation history.
So what are these variables? What do they represent?
There are two core types. The first type captures the content of the tape. We'll call it CGI-JAS dollar.
Okay, let me guess. Other dollars for content, dollars for time, dollars for space, others for symbol.
You got it. That variable is true if, at time step $I and tape position $, the symbol symbols is written on the tape. And we need one of these for every possible symbol at every single time-space coordinate.
Wow, that's already a lot of variables. What's the second type?
The second type pinpoints the machine itself. We'll call it HAJ. JJ.
H for head.
Yep. This variable is true if, at time $, the head is at position $, and the machine is in state $. This is how we track the machine's consciousness, so to speak.
So between the C variables and the H variables, we can describe the complete state of the machine at any instant.
And the entire computation becomes this one massive logical formula, which the sources call FINOS. And it's built from 5 main parts, all joined together with A and Ds. You need the cell part, and the head part, and the start part, and the move part, and the accept part to all be true.
Let's break those down. The first two sound like they're just setting up the rules of the universe. Structural integrity.
That's a perfect way to put it. Before we even care about what the machine is doing, we have to make sure the table we built even makes sense as a historical record. So, part 1, the cell formula.
This must be what makes sure the tape content isn't nonsensical, like having 2 different symbols in the same spot at the same time.
Exactly. For every single cell, grayish in our matrix, the cell formula enforces 2 things. First, a giant OR statement that says at least one symbol must be present. Some CIJOS has to be true.
Okay, that's the something is there rule.
And second, a whole series of clauses that say at most one symbol is present. So for any 2 different symbols, S to $and 22, you can't have both CIJS, DEOTS together, and CIJAS be true at the same time.
Got it. 1 symbol per cell, no more, no less. And I'm guessing part 2, the head formula, does the same thing for the machine's state.
Precisely. It guarantees that at every time step in every row, there is exactly one head in exactly one position in exactly one state. It prevents paradoxes. Without these 2 parts, the formula might be satisfiable, but the solution wouldn't represent a coherent computation.
Okay, so the physics of our computational universe are set. Now we need to inject the specifics. Start and the end.
Right. Part 3 is the start formula. This one's actually pretty simple. It's just a big AND of literals that locks in the initial configuration at time 1. It forces the head to be at position 1 in the starting state, $.
And it writes the input onto the tape.
Yep. It dictates that for row $1, the tape contains the input word, $6 through $6, followed by blank symbols everywhere else. It sets the initial conditions.
And then part 4, the accept formula, must define what success looks like.
It's the goal. It's just one huge OR statement. It says that somewhere in this entire matrix, for some time $, and some position $, the accepting state, text for step, must appear. The variable $parse has to be true somewhere.
Okay, so we have the structure, the start, the goal, but we're missing the most important piece. The thing that ensures that row 2 is a valid consequence of row 1, and row 3 falls from row 2, and so on. The actual movement.
That's part 5, the move formula. This is the heart of the whole construction. It's the engine that ensures every transition in the matrix strictly follows the Turing machine's own rulebook, its transition function, delta cell.
This feels like the part that could get really messy. If you have to write a logical rule for millions of possible transitions, how do you keep the formula from just exploding in size?
The sources all emphasize one critical insight: locality.
Locality.
A Turing machine is an inherently local device. What happens at time 1 plus $, at some tape position $, depends only on what was happening at time in a tiny little window right around position $.
You only need to look at the cell itself and maybe the ones next to it.
Exactly. You only need to look at the 3 cells, JJL1ers and $+ plus Noble 1. So we don't need a massive global rule. We just need to write a small local rule for every 3-cell neighborhood, for every step in time.
So the formula becomes a huge AND of all these little local consistency checks.
That's it. For every 3-cell window, at every time would force the rule. The configuration of this window at time, 2R plus 1, must be a valid consequence of its configuration at time.
So let's trace that. If the head isn't anywhere near that window at time.
The rule is simple. Nothing changes. The contents of those 3 cells at time I plus other must be identical to what they were at time $.
Okay, that preserves the rest of the tape. But if the head is in that window,
then the formula has to enforce the machine's transition rule, deltas. If the rule says when in state dollar reading symbol, right symbol, move right, enter state time, then the formula forces the variables for the next row to reflect that. It would say something like ACJ quiz is true, ACJJ is true, then ADCA plus 1, but JJ must be true, ADAJ plus 1 Dickles must be true.
And because you only have to encode these small local changes, the total size of the move formula doesn't explode. It stays polynomial.
It's proportional to the size of the matrix, which is PVN times PON. It's big, but it's polynomial. And that's the whole game. The final formula of Fairban's is satisfiable if and only if the original Turing machine accepts the input.
And that proves it. SAT is the universal translator for hardness. The first domino has fallen. If you can solve SAT fast, you have a fast solution for any problem whose answer can be checked quickly.
A monumental conclusion.
Yeah.
And it sets the stage for everything that comes next.
So that's the heavy lifting. Proving hardness from the ground up, from the raw definition of a Turing machine. That's done. But surely computer scientists don't have to go through that whole ordeal every single time they suspect a new problem is hard.
Oh, absolutely not. That would be completely impractical. This is where the idea of the NP-complete family tree comes in. It's all about transitivity.
Transitivity, meaning the hardness can be passed down.
Exactly. Once we know for a fact that problem A is NP-complete, if we want to prove a new problem, B is also NP-complete, we just have to do two things. First, show B is in NP, which is usually the easy part.
Just show that a solution can be checked quickly.
Right. And second, we have to find a polynomial time reduction from A to B. If we can transform any instance of our known hard problem A into an instance of our new problem B, then B must be at least as hard as A.
So B inherits the hardness. And if it's an NP and it's at least as hard as an NP-complete problem, it must also be NP-complete.
And that's how the avalanche started. But SAT itself, in its most general form, is still a little unwieldy for these reductions. So the first step was to narrow it down, to standardize it.
Which brings us to CNF-SAT, conjunctive normal form.
A much cleaner format. A CNF formula is always an A and D of a bunch of clauses, where each clause is an OR of a bunch of literals, a variable or its negation. This uniform structure is way easier to map onto other things like graphs or numbers.
But there's a catch here, isn't there? The sources point out that if you just naively try to convert any old logical formula into CNF using standard rules like De Morgan's laws, the formula can blow up exponentially in size.
It can. And an exponential time conversion would violate the polynomial time reduction rule. The whole thing would be invalid.
I had to get around that.
With a very clever bit of logical engineering called the Sighton transformation. The trick is to stop aiming for perfect logical equivalence.
What do you mean?
Two formulas are logically equivalent if they have the exact same truth table. The Sighton transformation only aims for something called satisfiability equivalence.
Which means?
It just means that the original formula is satisfiable if and only if the new formula is satisfiable. They don't have to behave identically on all inputs, but if one has a solution, the other is guaranteed to have one too. And for NP completeness, that's all we care about.
So how does it work? How does it avoid the exponential blowup?
It introduces new auxiliary variables to stand in for the results of sub-expressions. Imagine you have a complex formula like ZDAL equals A, O, R, not B, and DC.
Okay, nested logic.
Instead of expanding the outside and says, let's create a new variable, Y $1 hour, that is equivalent to the inner part, not B and DC. Then he says, let's create another variable, Y $2 an hour, equivalent to the outer part, A or R, Y $1. The final CNF formula is just the A and D of all these little equivalence definitions, plus a final clause saying that Y $2 must be true.
Ah, I see. You're flattening the structure. You break a complex, deep logical tree into a series of simple, shallow, local rules.
And converting each of those little rules, like Y $1 is equivalent to not B and DC, into CNF is trivial. It only creates a few small clauses. Since the number of new variables you add is just proportional to the size of the original formula, the whole new CNF formula is only linearly larger.
Which is definitely polynomial. Okay, so CNF-SAT is NP-complete. We have our standardized starting point.
And now we can get even more specific. And in doing so, we find this incredibly sharp boundary line in complexity. This takes us to 3 CNF-SAT.
So now we're saying every single clause in the formula can have at most 3 literals.
Right. Is this probably easier? You'd think so, but no. 3 CNF-SAT is also NP-complete. You can take any longer clause and, using a similar trick with auxiliary variables, break it down into a chain of equivalent 3 literal clauses.
So the full hardness is preserved even with this tight constraint.
It is. And 3 CNF-SAT becomes this perfect tool. It's the central distribution hub. It's restricted enough that it's easy to work with when you're building new reductions, but it's still powerful enough to hold all the complexity of NP completeness.
And this is where we get to that fascinating boundary you mentioned. 3CNF SAT is hard. What happens if we tighten the screw just one more turn?
What if we restrict it to 2 CNF SAT? Maximum of 2 literals per clause.
And the whole thing just collapses.
It completely collapses. 2 CNF SAT drops all the way down into P. It's efficiently solvable. There are well-known algorithms using things like implication graphs that can solve it in polynomial time.
That is just incredible. The razor's edge between a problem we think requires literally astronomical time and one we can solve quickly is the difference between 2 and 3.
It's a terrifyingly sharp boundary. It shows how fragile computational efficiency can be. Adding one single variable to a clause can catapult a problem from being trivial in a complexity sense to being a candidate for a Millennium Prize.
And because 3SAT sits right on that edge, it's the perfect launch pad for proving other problems are hard.
Which takes us from the world of pure logic into the world of graphs.
Okay, so 3SAT is our new weapon. Let's aim it at a new target. The independent set problem, or inset.
Right, inset. It's a classic combinatorial problem. You're given a graph, a bunch of nodes, and the edges connecting them, and a target number, $2. The question is, can you find a set of $2 nodes in that graph where no 2 nodes in your set are connected by an edge?
It's definitely an NP, because if I give you a set of $2 nodes, you can check really fast if any pair has an edge between them.
Trivial to check. So to prove it's NP complete, we have to show a polynomial time reduction from 3 CNFAs to inset. We need a recipe, a machine that turns a logic formula into a graph problem.
The goal being that the original formula is satisfiable if and only if the graph we build has an independent set of the right size.
Precisely. This is where the real creative engineering comes in. We're encoding logical contradiction as a physical connection, an edge in a graph.
Let's walk through the construction. Say our 3SAT formula has not clauses.
Then the first thing we do is set our target size, a killer, to be equal to 9. This is a huge clue. The goal is to select exactly one something for each of the original clauses.
So how do we represent the clauses in the graph?
For every clause $C, which has 3 literals, we create 3 nodes in our graph, 1 node for each literal.
And then the first trick, the interclause edges.
Yes, we connect those 3 nodes, the ones corresponding to the literals in a single clause, into a triangle.
A triangle. Okay, I see it. Because an independent set can't contain any connected nodes, making them a triangle means you can only pick one of them for your set.
At most 1. And since we have no clauses, and we're looking for an independent set of size kilenge, we are mathematically forced to select exactly 1 node from each of those triangles.
It's a beautiful constraint. You have to try to satisfy every clause by picking one of its literals. But that's not enough. The choices have to be consistent across the whole formula. You can't pick X from one clause and not X from another.
And that's the job of the second set of edges, the interclause edges. This is the global consistency check. We go through the graph, and we add an edge between any 2 nodes that represent contradicting literals.
So if clause 1 contains the literal $6 and clause 5 contains the literal nego, you draw an edge between the node for $6 in the first triangle and the node for nego in the 5th triangle.
No matter where they are, this edge is a contradiction edge. It makes it impossible to select both of those nodes for our independent set. It enforces the rule that $6 cannot be true and false at the same time.
So the geometry of the graph now perfectly mirrors the logic of the formula. The triangles force 1 choice per clause, and the contradiction edges force those choices to be consistent.
It's an exact mapping. The search for a size and LH independent set is now identical to the search for a satisfying truth assignment.
Okay, let's just quickly run through the proof of correctness. It has to work both ways.
Direction 1. If the formula is satisfiable, then an independent set of size L must exist. So we start with a satisfying assignment. In every clause, at least 1 literal must be true. So for each of the clauses, we pick 1 node that corresponds to a true literal.
That gives us not nodes. And since we only picked 1 from each triangle, there are no internal edges connecting them.
And more importantly, because the assignment is globally consistent, we could not have possibly picked a node for $6 and another node for nuller node. If we had, the assignment wouldn't have been satisfying in the first place, so no contradiction edges are violated either. The set is independent.
Perfect. Now, direction 2. If an independent set of size exists, the formula must be satisfiable.
Right, so we're given this set of no nodes. Because of the triangles, we know it must contain exactly 1 node from each of the not clause gadgets.
So we can define a truth assignment based on that?
We just say, For every no in our independent set the corresponding literal to true. First, is this assignment consistent? Yes, because if we had chosen nodes for both 6 BOS and 1 GRAX, there would be a contradiction edge between them, and our set wouldn't be independent.
So the assignment is consistent. And is it satisfying?
Well, we pick one literal node from every single clause triangle and set that literal to true. So by definition, every single clause is satisfied.
The equivalence is perfect. And the construction of the graph is fast. The number of nodes is just 3 times the number of clauses.
A simple polynomial time reduction. And just like that, the property of hardness propagates from logic into the geometric world of graphs. S@ leads to 3S@, which leads to inset. And this same basic technique is the foundation for proving that tons of other graph problems like click or vertex cover are also NP-complete.
Okay, we've conquered logic and we've conquered graphs. The family tree is growing. Now we move to a totally different feeling domain, simple arithmetic.
This is maybe my favorite branch. We want to show that this same fundamental difficulty, this NP-completeness, lives inside problems that just look like simple sums. Our target here is the subset sum problem.
Subset sum. Given a set of numbers and a target number, can you find a subset that adds up exactly to that target? It sounds like something you'd give a kid in math class.
It does. And checking a solution is trivial. You just add up the numbers, so it's clearly an NP. But proving it's NP hard requires what I think is the most ingenious reduction in the entire field. You're mapping abstract logic onto a positional number system.
You're encoding logic into digits.
We're going to build these huge numbers where each place, the ones place, the tens place, the hundreds place, carries a specific piece of logical information. We're turning addition into a kind of physical logic gate, where a carry from one column to the next represents a failure of the logic.
This sounds wild. Let's lay out the construction. We start with a 3SAT formula, say it has one any variables and a long clauses.
Okay, so we need to construct our set of numbers, CL dollars, and our target sum, $50. To do that, we imagine a giant spreadsheet. It's going to have ton of columns for the variables and no columns for the clauses. The variable columns will be the most significant digits, the ones on the left, and the clause columns will be on the right.
So each number we build will have 10 plus n other digits.
Basically, yes. We'll use base 10 just to make it easy to talk about. Now, first, we create the numbers that represent our choices. For every single variable, we create 2 numbers. One we'll call AI, which represents setting ADLs to true, and another one, a negi, for setting it to false.
What do these numbers look like?
This is the first constraint. Both of them, ADL not AI, get a 1 AL in the AI60 variable column.
Okay, so they both activate that variables column. What about the clause columns on the right?
There, we put a 1 if that specific literal appears in that specific clause. So if the literal $1 is in clause 3, the number $A gets a 1 in the clause 3 column. If $1 is in clause 5, then $A gets a 1 in the clause 5 column.
So the very structure of the formula is now written down in the digits of these numbers. Okay, now for the target sum, $. This must be the enforcer.
It's the enforcer. The number dollars is constructed to have 1s in all dollars of the variable columns and 3s in all no dollars of the clause columns.
Let's unpack how that works, starting with the variable constraint, the ones on the left.
Because the target sum dollar demands a 1 in every variable column, and since both the true and false numbers for a variable contribute a 1 to that column, we are forced to pick exactly one of them for our subset.
Right. If you pick both, the column sum is 2, which is wrong. If you pick neither, the sum is 0, which is also wrong.
So just by requiring the sum to match ballers, we've automatically enforced a perfect, consistent truth assignment. For every variable, you have to choose true or false, but not both. It's a beautiful mapping of logic onto arithmetic.
Okay, that handles consistency. Now, the clause fulfillment constraint. Why the 3s on the right?
Well, we started with a 3SAT formula, so each clause has 1, 2, or 3 literals. When we pick our subset of numbers based on a satisfying assignment, the sum in a clause's column will be 1, 2, or 3, depending on how many of its literals we set to true.
But the target is exactly 3. So if our chosen literals only add up to 1 or 2, we have a problem. We're short.
And that's where the final piece of the construction comes in, the filler numbers. For every single clause, 6 CJ$, we add 2 more little numbers to our set. Let's call them CJ$ and D$. Each of these numbers is all zeros, except for a single 1 in the CJ$ clause column.
They're slack variables, or slack numbers.
Exactly. Think of them as padding. If the literals you chose for a clause already sum up to 3 in that column, great, you don't pick the fillers. If they sum to 2, you pick one filler number to make it 3. If they sum to 1, you pick both filler numbers to make it 3.
And what if the clause isn't satisfied at all, meaning none of its literals were chosen? The sum in that column starts at 0.
And even if you add both filler numbers, the best you can do is $0 plus 1 plus 1 plus 2, 2. You can't reach the target of 3. So a failure to satisfy the clause logically translates directly into a failure to achieve the target sum arithmetically.
It's an airtight mapping. But there's that one subtle critical engineering detail you mentioned, the absolute need for no carryovers between the columns.
This is the secret sauce of the proof. If adding up the numbers in the clause columns on the right created a carryover into the variable columns on the left, the whole thing would break. The logic would get mixed up.
So we have to make sure the sum in any single column is never 10 or more.
Let's check. What's the maximum possible sum in any clause column? You could have at most 3 literals from the variable numbers, and you have 2 filler numbers. So the max sum is $3 plus 1 will equals 5 final.
Ah, and since 5 is less than 10, there can never be a carryover. Each column acts like its own independent little machine, enforcing its own local constraint.
It's what makes the proof work. The ones in the target guarantee a consistent assignment. The 3s guarantee every clause is satisfied. And the no carryover property guarantees that those 2 systems work in parallel without interfering with each other.
And so the conclusion is clear. If the formula is satisfiable, we can pick the right numbers to sum to bala dollars. If a subset sums to ballers, it must encode a satisfying assignment.
Which proves subset sum is NP complete. The hardness is propagated all the way from abstract machines, through logic, through graphs, and now into basic arithmetic.
So we've completed this kind of holy trinity of NP completeness propagation. We started with the origin in logic with SAT and the Cook-Levin theorem.
We showed it propagating into geometry and graphs with the reduction to independent set.
And now we've seen its reach into arithmetic with subset sum.
And you have to realize we've only scratched the surface. These 3 domains, logic, graphs, and numbers, they act as the main distribution channels for proving that thousands of other problems are NP complete.
Things like the traveling salesperson problem,
The knapsack problem, scheduling problems, facility location, circuit design. The list is enormous.
So the biggest takeaway here for you, the listener, is this mind-bending concept of equivalence. That all of these problems, whether they feel like routing trucks or folding proteins or solving a logic puzzle, they are all, in a deep mathematical sense, the same problem.
They are the hardest problems in NP, and they will all stand or fall together. If a researcher anywhere in the world finds an efficient, polynomial time algorithm for just one of them,
they have instantly found an efficient solution for all of them.
let's make that concrete. Imagine some grad student discovers a revolutionary algorithm for the bin packing problem. How to fit items into the minimum number of boxes. And let's say it runs in 1 hour time.
A fast, efficient algorithm.
That dollar blueprint could be taken, and through these chains of reductions we've been talking about, it could be reverse engineered. It would mean we could solve subset sum in polynomial time, which means we could solve 3 SAT in polynomial time.
And since SAT is the universal problem for all of NP,
it means that students' bin packing algorithm has just become a polynomial time algorithm for every verifiable problem. They would have proven P equals NP, won the $1 million prize, and completely rewritten the known limits of computation.
which is why proving a problem is NP hard is so important in the real world. It's a sign that says, stop looking for a perfect, efficient solution. It probably doesn't exist.
Right. Tells you to shift your focus to finding good enough solutions, heuristics, approximations, or finding special cases of your problem that might actually be easy.
Okay, so the P versus NP question remains this great, tantalizing unknown. We have this massive class of equivalent hard problems, and we strongly suspect they are genuinely intractable. But while we can't prove that gap between P and NP, we can prove a separation somewhere else in the hierarchy.
We can. We know the complexity hierarchy is structured something like this. P is contained within NP, and NP is contained within a much larger class called EXP for exponential time.
And EXP includes problems solvable in time, like down in $2 truly enormous amounts of time.
And while we only suspect that P is not equal to NP, we can definitively prove that P is not equal to EXP. This is crucial because it proves that these complexity classes aren't just arbitrary theoretical boxes. They represent real, provable differences in computational power.
The theorem that establishes this is called the time hierarchy theorem, but let's look at the result. P is a proper subset of EXP. There are problems out there that we can solve in exponential time that are provably impossible to solve in polynomial time.
And the proof uses a beautiful classic technique called diagonalization. It's a proof by self-reference and contradiction, very similar in spirit to the proof of the halting problem.
So what's the problem we use to show this separation?
It's a bit of an artificial problem constructed just for the proof. Let's call it Schalt index XP.
Okay, what does it ask?
It takes an input, which is the index of a Turing machine, $2, and it asks a simple question. Does the ionth Turing machine, Nithrin, halt on its own description within a very specific time bound, $2 steps?
So it's a version of the halting problem, but with a time limit. Why is that time limit so important?
Because it makes the problem decidable. The original halting problem is undecidable. There's no algorithm for it at all. But for Schalt index OSERV, we can solve it. We just simulate the machine, same knowledge for exactly 2 other steps. If it has halted by then, the answer is yes. If not, the answer is no.
And since simulating for $2 steps takes exponential time, this problem is clearly in the class EXP.
It is. So we know Schalt index XP is an EXP. To prove P is not equal to EXP, we just have to prove that this problem cannot be in P, and we do that by contradiction.
We assume it is in P, so there exists some super fast polynomial time Turing machine, let's call it memtex, that can solve it.
Right. And if memtex knows this, we can use it to build a new machine, a villain machine, let's call it memtex. This villain is specifically designed to contradict the prediction of our supposed solver.
Walk me through the villain's logic. It takes an input, dollars, and its first step is to use our hypothetical fast solver and analyze dollar.
Yes. It asks Zemmenzellers for prediction. Will the machine described by dollar halt within $2 of steps? And then the villain machine does the exact opposite of the prediction.
How so?
The logic is inverted. 1. If memtex predicts yes, it will halt quickly, then our villain machine deliberately enters a long loop and runs for more than $2 steps before halting.
It intentionally runs long to make the prediction wrong.
And 2, if memtex predicts no, it will run for too long, then our villain machine halts immediately.
It runs short to make that prediction wrong, so it's a machine built to disobey its own analysis.
It's a paradox machine. Now, this villain machine is a perfectly valid Turing machine, so it must have an index number in our list, say index dollars. And now for the diagonalization step. What happens when we feed the villain machine its own description $2 as input?
Oh, this is going to get weird. We're asking the machine to analyze itself. So we ask, does the villain machine $dollar halt within $2 steps when given its own code as input?
Let's look at the 2 possibilities. Case 1. Assume our villain machine halts quickly. Well, for that to be true, our magical solver must have predicted yes. But what does our villain machine do when it gets a yes prediction?
It's programmed to run long, longer than $2 steps. That's a flat-out contradiction.
Contradiction, so that can't be true. Okay, case 2. Assume our villain machine $3 runs long. For that to be true, our solver Emish was predicted no. But what does the villain machine do when it gets a no prediction?
It's programmed to halt immediately. To run short, another contradiction.
The total paradox. The only way to resolve the paradox is to conclude that our initial assumption was wrong. The hypothetical polynomial time machine, Emmy's sheet, cannot possibly exist.
And if that machine can't exist, then the problem it was supposed to solve, Schalt index XP, cannot be in P.
And since we know that problem is in EXP, we have found a problem that is in EXP, but not in P. Therefore, P is a proper subset of EXP. They are not the same class.
The implication is massive. We've anchored the hierarchy. We know for a fact that there are different levels of difficulty, and the gap between polynomial and exponential time is real and provable. It lends so much weight to the suspicion that NP-complete problems, which sit somewhere in between, are also genuinely harder than P.
We have proven a genuine, necessary separation. We know P is inside EXP, but it is not equal to it. This confirms the gaps in the complexity hierarchy are real, and most experts in the field suspect there are actually 2 distinct gaps, one between P and NP, and another one between NP and EXP.
So if both of those gaps are real, it would mean that problems like solving gigantic games of chess or checkers, which are in EXP, are fundamentally harder than problems like the traveling salesperson or SAT, which are in NP.
Which are themselves, in turn, fundamentally harder than problems like sorting a list or finding the shortest path in a simple graph, which are in P. You now have the map of the entire landscape.
So for you, the learner, the key takeaways from this journey are those foundational proofs. The way Cook and Levin encoded time and space into pure logic. The way a logical contradiction can be transformed into a physical edge in a graph. And that incredible feat of engineering enforcing logic using positional arithmetic in subset sum.
You now understand the deep profound mathematical equivalence of the hardest computational problems that we know of.
We know P is not EXP. We strongly suspect P is not NP. But that central mystery, that billion-dollar question, remains. We've shown this entire family of NP and P problems are locked together, an unbreakable chain of computational bottlenecks.
But what if?
Mm.
What if we're all just wrong about P not equaling NP? What if the key to unlocking this entire class of problems isn't some brand new esoteric field of mathematics, but simply the discovery of a single, specific, efficient algorithm that's been hiding in plain sight for decades?
An algorithm that's maybe just 10 lines of code. A subtle, clever reorganization of how we search for solutions, just waiting for someone to type it in. That tiny breakthrough wouldn't just win $1 million. It would instantly revolutionize optimization, logistics, drug design, cryptography, and artificial intelligence. It would prove that the boundary we see between the easy and the impossible wasn't a law of nature, but merely an oversight in human ingenuity. That is the true prize, waiting for the person who can unlock the secret of the NP-complete family.